Hello everyone, I am Ahmet Selim Ayaz from Physics Department, and today I'm going to present our modern physics project, which is named Qualitative Noise Comparison between analogous, classical, and quantum operators. Our main objective was to investigate how noise accumulates in two completely different domains, a classical electrical circuit and a quantum qubit system. To do this, we focused on a fundamental quantum operator, the Hadamard gate, which is named after French mathematician Jacques Hadamard. Unlike classical bits, qubits can exist in a superpositional state. The Hadamard gate is the matrix operation responsible for transforming a definite state into a balanced superposition. Mathematically, it looks like this. A fascinating property of this unitary operator is that applying it twice gives us the identity matrix h squared equals identity. This means two consecutive operations should theoretically return the system back into its original state. We use this property to build and compare analogous systems. Let's start with the quantum setup. Utilizing the Qiskit library on the IBM quantum platform, we constructed a 5-qubit circuit. We applied 1, 3, 5, 7, and 9 consecutive Hadamard gates to these qubits respectively. Here we faced an interesting software challenge. Quantum compilers naturally try to optimize circuits. If it sees multiple Hadamard gates, it might combine them to save runtime. To prevent this and measure the pure noise of the individual gate, we had to deliberately implement barrier operations between them. For the classical analog, we designed a circuit using LM224 op-amps to exactly like a Hadamard gate, utilizing summing and difference amplifiers with a resistance ratio of 1 over square root of 2 to simulate the normalization. This is where we hit a major hardware challenge. Initially, we used breadboards, but the parasitic noise caused by the contact resistance completely violated our qualitative noise comparison. To solve this, we moved to a soldering board, meticulously soldering all components to ensure high fidelity. Furthermore, our first prototype only worked when one of the inputs was zeroed. We had to redesign a general's difference operator to make it function properly for any given input. To interpret the electrical voltages as quantum probabilities, we used an analogy based on Born's rule. We measured the output voltages V0 and V1 and calculated the probabilities, which we refer to as fidelity, using the amplitude squared. In our electrical circuit, looking at the odd-numbered operations 1, 3, 5, and 7 gates, the noise continuously increased from 4% up to 12%. However, when we looked at the even-numbered operations 2, 4, 6, and 8 gates, the noise was drastically lower, hovering around 0.15% to 1.18%. This proves our theoretical baseline. Since an even number of Hadamard operations acts as an identity operator, the electrical circuit effectively neutralizes the transformation-induced noise, returning to a stable, deterministic state. When we compared the two domains, we found a surprising result. The primary noise levels of the electrical data were actually higher than the quantum data. For instance, the maximum noise in the 9-gate quantum operation was only 1.907%. So we asked why? Why did this happen? While we expected quantum technologies to be highly unstable and chaotic due to their indeterministic nature, our classical circuit suffered from severe heat dissipation. The sheer number of resistors required for normalization heavily contributed to energy loss, clouding the stability of our classical system. On the quantum side, however, the noise originates from completely different physical phenomena, like energy leakage and decoherence. The quantum gates don't just cancel out their physical errors when acting as an identity matrix, they continue to interact physically and accumulate stochastic errors. Yet, despite this neutralization effect, when we compare the two domains overall, our classical circuit actually had higher noise in the odd-numbered states compared to the quantum data. For instance, the maximum noise in the 9-gate quantum operation was under 2%. This highlights a major practical limitation in our hardware realization. To normalize the signals in our analog circuit, we had to heavily rely on resistor voltage dividers. It shows us that while classical circuits can simulate quantum logic, the physical overhead of forcing a classical system to normalize like a probability amplitude leads to a significant cumulative noise. So in conclusion, both systems exhibited the greatest noise when the highest number of operators were applied, validating our methodology. While quantum technologies still face challenging with indeterministic stability, our project demonstrates that classical energy dissipation currently limits the reliability of building a perfect analog electrical operator. Finally, special thanks to Sebahattin Erarsan, Ali Joya, and my group members Eda Ayvaz and Mehmet Arda Yıldırım. Thank you for your attention.